All right, so I was just talking to Sandra about some of the SmartWork stuff, and I've got my desktop shared here, so you should be able to see what I'm doing. Although apparently I heard from some other folks that can be kind of choppy. So this will be recorded in a much better format, so you can watch it later if it's really choppy for you on your screen. But I wanted to talk a little bit about the SmartWork stuff. For a second and how you can do that a little bit more effectively. First of all, let me talk about a place called Study Space, which is at www.norton.com/studyspace. So these are some resources that come with your text, and if you zoom down or scroll down to your textbook, which is Understanding Our Universe, which is near the bottom here, right here, you can click on Enter Study Space. And there's a whole bunch of stuff that you can use here to help you out with the SmartWork. There's a link to the SmartWork, so you can log on to that. There's some things called Astro Tours, which have sort of narrated descriptions of some of the material. So, for example, if you wanted to know more about the celestial sphere and the ecliptic, you can watch that. And if I open that up, it starts a little
Ancient
slideshow
peoples were fascinated by
that talks a little bit more about that. So there's just some things chapter by chapter. There's some simulations that we'll be using in the homework, and then there's the astronomy news links, which we also have some of those in SmartWork. So this is a good resource to go and learn a little bit more about those things. But when you're doing SmartWork, the way that you want to approach this is it's very much based on the text. So if you do the reading and maybe go to some of the Astro Tours that are in that chapter, the SmartWork should be a lot more approachable. What I would recommend you do is, and this is what I do when I do homework like this in other classes that I take, is read through the questions in SmartWork first. Don't answer them, just read through them, and then you can go back and start your reading, and you have an idea of what to look for. So that's what I would recommend with SmartWork. Does that give you some ideas? And feel free to just type questions in the sidebar here if you've got them. Okay, so that's SmartWork. And the other thing I wanted to show you is just on our website, the way I've organized this class is through Canvas is maybe not the most efficient way of doing it. I'm trying to see if there's a better way of doing it. Unfortunately, in Canvas, to get things to show up on the calendar, you have to add them as assignments. And I have things that I want you to know about on the calendar, like the when the activities are due and when the topics are due. But then if I were to add in all of the stuff for SmartWork, that would kind of clutter up this syllabus, which is already pretty cluttered. So I'm leaving SmartWork as a separate website that you'll just have to check to see when the assignments are due. And hopefully that will become clear as we go along. So when you want to see what you need to do for the class, what I would do is come to the Canvas website and go. That'll take you straight to the course syllabus. If you go down all the way to the bottom, you'll see what we're doing on any given day. The activities, I'm pretty flexible about the due dates on the activities. So when I say they're due, what I mean is that we've been talking about this stuff. I'd really like to get them in. I won't grade them until I get everybody's in, so they are due when we say they're due. But if you don't get them in right at 9 a.m., I'm not too worried about that, especially if you've got questions. Okay, so the two activities that you should be working on today are the finding things in the night sky using Stellarium and the cause of the seasons. And those two activities should take you about an hour to do. I don't think they should take a whole lot of time. The finding things in the night sky, it's helpful if you have a friend to help you out. The cause of the seasons is something you can do on your own. Okay, so any questions before we get going? Oh, I got a question from Shay here. So Shay just asked, so we don't have to answer the questions when we go into SmartWork. You can just read the questions, exit, go out, and read the book. Yes, Shay, that's true. You do need to go back and answer the questions to get credit, but you can go in and read them and then leave, and then come back and answer them later, right? So you don't need to do the entire SmartWork all at once. You can go in there. You can review some of the questions, you can exit out, you can come back in and do whatever you like. It's not until you hit that submit button that the grade is recorded. Okay, so yeah, absolutely. I would go in and read them and then go and think about them. Generally, what I recommend people do is, go look. If you've got a SmartWork due on next Thursday, read those today, and then you've got a whole week to kind of let them just sort out in your brain while you go through some of the material. All right, so if there aren't any other questions, there's just a couple of us here today, which is nice. Nice to have some folks here. It's a difficult time to make, I realize. Before I go on, just I noticed that everybody finding the videos okay, I hope. To find the videos, you just click on the topic we're interested in, and you should see the video there if I've already recorded it, and you'll find the lecture notes there as well. And those will be populated as we go. So today's activity, or today's topic, Kepler's laws, doesn't have the video on yet because I haven't edited this and put it up there, but I do have the notes we're going to use today for Kepler's laws. Okay, so we want to talk today a little bit about how planets move around the sun. And there's a couple of different ideas for how this works. If you go into a planetarium program like Stellarium, or if you go outside and look at things, it sure looks like the stuff all moves around us, right? The sun rises in the east, sets in the west. The moon rises in the east, sets in the west. All the stars do the same thing. So the obvious solution to that problem is that the Earth is stationary and everything's going around us. We all know that's not true, but that's not a completely illogical position to be in. And people thought that was true for quite some time. They had this idea of a geocentric model, right? Ptolemy was the guy who first proposed this, that you would have the Earth at the center, and you would have the sun going around the Earth, and you'd have everything else going around the Earth. Now the problem with that, and let me see if I can draw a little picture here to sort of illustrate this. The problem with that is that, let's say I put the Earth in the center here, right? So here's the Earth, and then I put the sun going around the Earth. Right, this is our geocentric model, and here's the Earth in the center. The problem with that is that if I put the moon going around the Earth, that's okay, but there are these planets, Venus and Mercury, that look like they never get too far from the sun, and in fact, if you look at them, they have phases, which indicates they're going around the sun. So you've got Venus and Mercury. There's Venus and there's Mercury going around the sun, and then you've got things like Mars out here, and you've got Jupiter out here, and so you have this incredibly complicated model for something that should have been a simple thing, right? So we've got this very complicated model where the Earth is definitely at the center, which seems to be logically what should be happening, but we have to do all this funny stuff to the model to get that to work. So some folks came up with a different idea. The different idea was something called the heliocentric model, and this was Copernicus's contribution. And Copernicus was the guy who said, look, why would we be at the center of the universe if we have the Mercury and Venus going around the sun? Why doesn't everything else go around the sun? And so he had the idea of a heliocentric model. The sun at the center right here, this is the sun now, and you've got Mercury going around the sun, you've got Venus going around the sun, you've got Earth going around the sun, right? You've got Mars going around the sun, and everything is centered on the sun. Is a very simple model, right? The only problem with this is that Copernicus thought these were perfect circles, and these perfect circles didn't match the data of the planetary motion any better than this complicated geocentric model from Ptolemy. And so they had this problem where they had these two competing models that didn't match the data. You couldn't tell from the data which one was correct, right? So the data was telling you, wasn't able to distinguish between these two models. And they would have a whole bunch of arguments about which model should be which. Copernicus would say, well, my model's simpler, so we'll use that. Folks who follow Ptolemy would say, well, I can feel the Earth stationary under my feet. It doesn't make any sense, because I didn't know about gravity at that time, to have the Earth going around the sun, because then we have to spin the Earth and then we'd all fly off. So there was a long debate for quite a while about which one of these two models was correct. So finally, a guy by the name of Kepler came along to put forth the heliocentric model with one small change, and that small change was he used, instead of circles for the orbits, he used something known as ellipses. And this was one of those things where he just kind of made it up. He said, circles don't work. If I try ellipses, they match the data better. He didn't have any reason why they should be on ellipses. He just said, look, they must be ellipses because they match the data better. So these are Kepler's laws. Kepler came up with these again by just making the kind of logical leap from circles to ellipses, and he found that it matched the data much better than previously. And again, he didn't have any reason why they should be on ellipses, but he found that when he used ellipses, it matched the data. So it became a model without a reason, and a little bit later we'll get to the reason. The reason happens to be gravity. We need Newton for that. Okay, so first let's remind ourselves what an ellipse is. An ellipse is a geometrical shape that looks like kind of like an egg, and it has two dots in the center that are the different foci of the ellipse. And if you want to make an ellipse, all you have to do is stick two thumbtacks into a sheet of paper, right? And then put a little string around it, put a pencil on the string, and then draw with the pencil, and you will get an ellipse, because those strings will stay tight around those two pens as you're going around, right? So you'll get an ellipse. And a circle is a special kind of ellipse where both foci are in the center. So if you take both of those foci, move them to the center of the ellipse, then you have a circle. There are two parts of this ellipse. There's the minor axis that goes this way, and the major axis. Yeah, so I got a question down here that says, yeah, any distance between the tacks. Yeah, if you make these distances between these tacks bigger, so let's say I take this tack and put it over here, and this tack and I move it over here, and I do the same thing, I'm just going to get an ellipse that looks, if I use the string, same string I used before, I'm going to get ellipse, but it's going to look like this. Right? So it's going to be an ellipse still, and then my drawing isn't all that great, but it's still going to be an ellipse. It's just going to be squatter and longer. So yeah, that's, you can, if you move those foci apart, you get a squatter ellipse. If you move those foci together, you get a narrower ellipse, and you wind up with something that that looks like a circle. Okay, so the major axis, and what Kepler said, and this of course had, he had no reason again for why this was, but he said, look, the sun is going to be at one of the foci right there. There's nothing at the other one. And of course, you know, people thought, well, that's kind of weird, but it turns out gravity explains that. And then the planet goes around on this ellipse like that. Okay, so you have a planet up here that goes around. So that's Kepler's first law, just that we have ellipses, and that's how planets work, that they orbit on ellipses. And we define the semi-major axis, that's this word over here. The semi-major axis is half of the major axis, right? That's half the major axis, and half the major axis is the average distance between the planet and the star. So if the star is close, this is called perihelion, and we've got some, I think I've got this on a slide later, but this is called perihelion. That's this point right here, that's the closest point, and then we have aphelion. These are Greek words for close to star and far away from star. So this is a big distance here, right? That's the furthest distance the planet gets from the star. This is the closest distance, and the average of those two is the semi-major axis right there. Okay. So that's Kepler's first law, ellipses, right? His second law had something to do with how the planet moves on these ellipses. And this was something that, again, was motivated by watching the motions of the stars, watching the motions of Mars and Jupiter. And he noticed that when this planet was closest to the star, right here, that it moved faster. And that's indicated by the length of this arrow. So this arrow is long when we're at the closest point, right? That arrow is long, which means it's moving faster. And when it's further away, this is the furthest point away, it's moving slower, and that's represented by the smaller arrow. So it moves fast over here when it's close, and slow over here when it's far away. And again, he didn't know why, but that's what he observed, right? And it changes its speed as it goes through the orbit. Now, the way that Kepler phrased this thing about the speeds is he said that planets sweep out equal areas in equal times. And what that meant is that if you drew a line from the star to the planet at any point, and then you let some time elapse, you know, like say 10 days or something like that, then you could create a little geometric shape here that had a certain area, and you can, shade that in, and that's a certain area that the planet swept out. And then if you did that again, if you took a line from the star to the planet and then waited the same amount of time, 10 days let's say, then that shape would have the same area as this shape. So those two areas would be equal, and that's what he called the equal areas law. He said that the planet sweeps out the same area in the same amount of time. And all that really means is that if you're far away, right, you've got a long line to your planet and a long line to your planet, and so you got to make this side short because that area has to be the same as when you're close, and you move faster, so you've got two short lengths of this shape, and so that makes a longer shape here, which means you have to move faster on the orbit. So that just means you're moving slow over here and fast over here. And if Kepler was alive today, he would probably call his second law the different speed law or something, but he wrote it out as planets sweep out equal area in equal time. All right, so that's his second law. For some reason, people like laws in thirds, and so we have Kepler's third law. And this was really cool because Kepler was the first person to put a scale on the solar system, because he said that if we could measure the semi-major axis, and the semi-major axis, because we didn't really know how big it was at the time, he just called an astronomical unit, right? So the semi-major axis from the Earth to the Sun is 1. If we can measure that, and we could measure the orbital period, so how long it takes this planet to go around the Sun, in the case of the Earth it's 1 year, then that would, there was a mathematical relationship between those two quantities, and that mathematical relationship was this one. P squared equals r cubed. This is Kepler's third law. And all it means is if you measure the period, right, so the example for the period is that the Earth is 1 year. I take 1 year and I plug it in there and I square it. 1 squared is 1. I take 1 astronomical unit and put it in here. 1 cubed is 1. 1 equals 1. The relationship holds. All right, so that's trivial because it's for 1 and 1, but it works for any planet. You put in Mars. Mars has a semi-major axis of, Mars has an R of 1.52, and it has a period of something like, I can't remember Mars's period. Well, we can figure it out from this, right? If I take r cubed, let's just do this since I've got my Google calculator here. Let's go to my Google calculator. If I say 1.5 cubed, right? And I don't know if you knew that Google was a calculator, but it is. If I take 1.5 cubed and then take the square root of it, square root of 1.5 cubed, I get 1.83 years, which is Mars's orbital period. So that works for Earth, it works for Mars, this relationship holds. I've got an example for Jupiter. Jupiter has a semi-major axis of 5 astronomical units, right? 5 astronomical units for the semi-major axis. If I look at taking that, take the 5 and I take it to the third power and then take the square root, that's the same thing, by the way, as saying 5 cubed square root. Might be a more familiar notation. So I take 5 cubed on this side, I take the square root, and I get 11.2 years, which is the orbit of Jupiter. So the most exciting thing about Kepler's third law is that he could know the periods, which are easy to measure. You can wait until Mars gets to the same point in space and find out how far away it is, at least relative to the Earth. So he set a scale. He was the one who figured out that if Earth is 1 unit from the Sun, Jupiter is 5 units from the Sun, which was something nobody ever knew before. And that was simply because of Kepler's law, Kepler's third law. Okay, so let's do a couple more little examples here. What about Pluto? So let's take a minute to figure out what Pluto's orbital period is. And again, we can use Kepler's law for this. I'm just going to fire up my Google calculator because I love using Google Calculator, because I can just type it into the search bar. I can say the square root of 40 cubed. And it gives me 253, which is right there. Go back here, 253, the answer is A, 253. It works for any planet in the solar system, even those planets that are no longer planets, like Pluto. Okay, questions about Kepler's laws? We can just review those real quick. Again, the first law, ellipses. Second law, the thing moves closer. When it's closer, it's faster. When it's further away, it's slower. That's the equal areas law. And then the third law is this wonderful mathematical relationship between the semi-major axis and the period. So this was the power of Kepler's laws. The crazy thing is he didn't have any explanation for why this was the way it was. It just happened to be the way it was. When we get to Newton's laws, we'll see that there is a reason why it is the way it is. It's called gravity. All right, the last couple things I want to mention here about Kepler's laws are perihelion and aphelion. These are these two quantities of the closest and furthest positions away. Those depend on the eccentricity. If you move those tacks apart, the eccentricity gets bigger, and the closest and furthest points change. So the way that you can think about this, if you look at the ellipse, we take the semi-major axis, which is, where's my semi-major? We take the semi-major axis, which is this guy right here. The semi-major axis, this guy right here. And we want to look at the closest part. This is the perihelion right here, and then we want to look at the farthest part, that's the aphelion right here. And you can already see that the perihelion is smaller than the aphelion, right? And so this guy has got to be smaller, and this guy's got to be bigger, and how small or how big they are depends on how far apart these foci are. If I make these things further apart, then that's going to make the perihelion smaller and the aphelion bigger, right? Because as we make the ellipse bigger, more elliptical, this moves to here. And so it's related to this thing called the ellipticity, which is a measure of how elliptical this thing is, and we call that E, the eccentricity, and it's a number between 0 and 1. 0 eccentricity is a circle, 1 eccentricity is a straight line. And so if we take 1 minus this eccentricity and multiply it by the semi-major axis, and I used A here because your book tends to use that, but let's, just for clarity, let's just make sure we know that this is the same as R times 1 minus E, because that's what we were using before, and R 1 plus E. So if I take the semi-major axis and multiply it by 1 minus E, I get the perihelion, and the aphelion is R times 1 plus E. So if E is equal to 0, I get a circle, right? Because 1 minus 0 is 1, 1 plus 0 is 1, and we return the same radius of this circle in both cases. The bigger I make E, the smaller perihelion is, right? If I make E 0.5, then this is going to be 1/2 of my semi-major axis. And if I make E 0.5 here, the aphelion is going to be 1.5, right? For the distance from the center, or from the center of the star. So I've got a couple of examples of that here. Let's do this for the Earth. Now the Earth is primarily circular, right? But it does have a small ellipticity. It has a small eccentricity of 0.017. I'm using the words ellipticity and eccentricity interchangeably, but the technical term is eccentricity. So to figure out the perihelion, right? The perihelion, just say peri, is going to be equal to the semi-major axis, which is 1.0 for the Earth, times 1 minus 0.017, right? That's the perihelion distance. And so that's got to be 1 minus some little bit. So if I look over here, the only ones that are 1 minus a little bit are, well, the only one that's 1 minus 0.017 is this guy down here, right? Because this is, if I add 0.017 to this, I get 1. So then I look at the aphelion. I get 1.0 is the semi-major axis for Earth, and then I say 1 plus 0.017, and that's going to be this guy right here. Okay, so the answer to that one is D. So the perihelion and aphelion distances are computable once you know the eccentricity. And the bigger I make the eccentricity, the bigger the difference in these two numbers. Okay. So just in summary for Kepler's laws, the planets move in ellipses around the sun, with the sun at one focus. The planets move faster when they're closest to the sun and slower when they're further away. That's the equal areas law. And there's a direct mathematical relationship between the planet's period and its semi-major axis, and that lets us compute the scale of the solar system. That's the power of Kepler's laws. And he got that simply because he was willing to relax some of the restrictions on the previous models. Okay, so the other thing I wanted to do today, if there are no other questions on Kepler's laws, is I wanted to discuss one of the activities that we're going to be using or going to be doing that looks at the motion of the planets. Now that we know how motions work, because Kepler's laws applies to the solar system, it applies to our Earth and Moon, we want to see if we can use observations to figure out the motions of the planets. All right, so this is the phases of the Moon activity, and what we're going to do is use this to figure out the motion of the Earth and the Moon and the Sun in our solar system, and these motions are used by Kepler's law. You have up here you have the observations of what the moon looks like throughout the entire lunar cycle. And you've probably seen the moon look like this. You go outside and you see what's called a waning crescent moon or a waxing crescent moon, or you don't see any moon at all. We call that a new moon. You've seen first quarter, waxing, full, and this is called a gibbous moon when it's between first quarter and full, waning gibbous, third quarter, waning crescent, and then it reverts back to here and goes through it again. So that's the lunar cycle. That's what happens when you look out and see the moon through the course of the month. And this is the order in which you would see those phases of the moon. And so your job with this activity is to work out how the moon actually moves around the Earth. Now, you know that the moon goes around the Earth, but from the phases you can tell the direction that it goes around the Earth, and also you can measure, if you measure the time between phases, how long it takes to go around the Earth. So your job, and this is you can do this on your own. It's easier if you have a couple people to help you, but you can do this on your own. What you're going to do is build a model of your Earth-Moon system. You can pretend you're the Earth. You can hold out a little ball or something like that to pretend it's the moon, and then you can put the sun as some object around, some lamp in your house or something like that. And when you take this ball and move it around, you're going to imagine that you're seeing the lit part of the ball as you go around, right? So if I've got a lamp right here. Everybody sees my lamp, that's my sun, so the sun is off to my right. If I hold out my hand like this, right, the moon is directly in front of me, and I'm looking directly at the moon, I can see that from my perspective, the right-hand side of the moon is lit. And if the right-hand side of the moon is lit from my perspective on the Earth, I can go up here and discover that that is the first quarter, right, because that's the right-hand side of the moon is lit. I come down here to this little drawing, and this is us looking down on the solar system, looking down on the North Pole of the Earth. I find the one that says first quarter, and I draw it. So I'll go ahead and do that. So I find the one that says first quarter, and I draw it. And because my sun was off to my right, I'm the Earth, and I was holding my hand out in front of me like this, looking down on the top of my head, I can see that this is where the first quarter moon is. Okay. So then I want to do another one. Well, the other easy one to do is the full moon. So if I have this, again, the sun is that way, and if I'm looking at it like this, here's my full moon right out in front of me. If I don't stand in the way of the light, I see that the entire moon is illuminated, so I know that's how I know it's full. Right? And then I can see that it's directly opposite of the sun. So I go again up to my observations here and I see the full moon. And I go down here to find out where it says full, and I draw that. So I know that the full was completely opposite the sun, like this. And then you can do that for third quarter, you can do that for crescent, waxing crescent, waning crescent, and fill in this whole map. And when you do that, because you know that this is the order of the phases, you'll be able to see exactly how the moon goes around the Earth. So that's the first part of this activity. The second part is using what you've just learned to figure out some things about, answer some of these questions about these observations that you made, but then also doing some things about what the Earth looks like, right, from these different models. So in this case, for example, I've got a view from the Earth which shows the moon, right? And I've got to figure out where the moon is up here. So you can match that back to your previous page, or you can do the dance again, do the model, and see where it is. For this one, I've got the Earth-Moon system, and I need to figure out what it looks like from the Earth, right? And same thing here. And then we have you go to Mars and do something similar. And then the really fun one is once you can see where the phases of the moon are and where it is in the sky, you can tell things like the time, right? You can tell the time from where you happen to be on the Earth and where the moon happens to be. So for this particular example right here, we have the phase here. You can probably tell me what the phase is. The phase is a full phase, because I knew that from back here. So this is full, so I can write down the phase here is full. And I can tell that the sun is opposite the moon. So wherever I'm talking about, the moon has to be on one side, the sun has to be on the other. And I know that the Earth, if I'm looking down on north, the Earth rotates counterclockwise, like that. So if I'm here, and I'm rotating counterclockwise, and I imagine my horizon sticking out like this, then that means that the sun, since I'm rotating this way, is on the western horizon, and the moon is on the eastern horizon, and that means that the time is around 6 p.m., because it has to be at sunset. So if you know where the phase of the moon is, if you know what the phase of the moon is, and you know where the moon is relative to the sun, you can figure out what time it is, which is pretty handy if you're ever outside without a watch and you want to figure out what time it is. Okay, so this is the activity I'd like you to do for next Tuesday, I think is when we're going to have that. And you can email me any questions that you might have.